A shooting star tears across the night sky, and in the half-second it takes your eyes to track that streak of light. A question forms in your mind that you may never have articulated before. How fast was that thing actually moving at the precise instant it vanished? Not its average speed over the arc you saw, not a rough estimate, but the exact velocity at one frozen sliver of time. The moment you try to answer that question honestly, you have stepped through the doorway of calculus, and the universe will never look the same again. Most people who went through high school or college remember calculus as a wall of symbols on a chalkboard, a procession of formulas to memorize, a mechanical ritual in which you learned that the derivative of x to the n equals n times x to the n minus 1, regurgitated the rule on a test, and then forgot it before the weekend. If that was your experience, you are far from alone. Surveys of American college students consistently show that calculus is one of the most dreaded courses in the curriculum, a gatekeeper that derails ambitions in engineering, physics, economics, and medicine every single year. Entire industries of private tutoring and online crash courses exist because the standard classroom experience fails so many people so thoroughly. And yet here is a fact that should stop you in your tracks. Calculus is arguably the single most revolutionary intellectual invention in the history of the human species. The physicist Richard Feynman, in a conversation with the novelist Herman Wouk, once called calculus the language God talks. That was not a throwaway line. Feynman meant it almost literally. Every equation that describes the trajectory of a rocket, every model that predicts the weather, every algorithm that routes a GPS satellite signal from 20,000 kilometers overhead to the phone in your pocket, every simulation that reveals what happens when two black holes collide, every calculation that tells an engineer how much stress a bridge can bear before it snaps, all of it is written in the language of calculus. Strip calculus out of modern civilization, and you do not merely lose a branch of mathematics. You lose the ability to build airplanes, to design semiconductors, to model the spread of a pandemic, to understand why the universe is expanding, to predict the orbit of the International Space Station, to run a power grid, to decode the structure of DNA, to price a financial derivative, to render a frame of a Pixar movie, to aim a spacecraft at Jupiter with enough precision to thread it through a gap in Saturn's rings 8 years later. Calculus is not a subject in school. It is the operating system of reality. So why was it so boring in that classroom? The answer is painfully simple. Traditional education teaches you how to perform the calculations, but almost never tells you why the tool was invented in the first place, or what it allows you to see that was invisible before. Imagine someone hands you a recipe for a dish you have never tasted, made from ingredients you have never smelled, and tells you to follow the steps precisely. You might execute the recipe correctly, but you will feel no passion, no curiosity, no delight, because you have no idea what you are creating. That is what most calculus classes do. They hand you the recipe and skip the feast. The feast is the universe. Calculus was born from a single desperate question. How do you capture something that never stops changing? An apple falls from a tree and accelerates toward the ground. At the exact moment it passes your eye, how fast is it going? A planet sweeps around the sun, speeding up as it draws closer and slowing down as it recedes. What force compels it to trace that precise curve? To answer questions like these, you need a way to freeze a single instant out of a continuous flow of motion and measure the rate of change at that instant alone. And here is where the trouble starts. Speed is defined as distance divided by time. If you drive 300 miles in 5 hours, your average speed is 60 miles per hour. Easy enough. But average speed tells you nothing about the instant you swerved to avoid a deer or the moment you floored the accelerator merging onto the interstate. To find the speed at a single instant, you need to shrink the time interval down to 0. And the moment you do that, you are dividing by 0, which is the one operation that mathematics absolutely forbids. The entire number system breaks if you allow division by 0. The answer can be anything and everything and nothing, all at once. This is the paradox that haunted the greatest minds on Earth for more than 2,000 years. And resolving it required an idea so subtle and so profound that it took the combined genius of dozens of civilizations to bring it into focus. The first people to notice the problem were the ancient Greeks. specifically a philosopher from the coastal city of Iliia in southern Italy named Zeno, who lived in the 5th century BC. Zeno posed a series of riddles that sound almost childish at first, but turn out to be intellectual time bombs that would not be fully diffused until the 19th century, more than 2,300 years after he stated them. The most famous of Zeno's puzzles is called Achilles and the Tortoise. Think of it as a foot race set up on a straight track somewhere in the American Midwest. Maybe a dusty quarter-mile strip in rural Kansas. Achilles, the fastest sprinter in the state, agrees to race a tortoise. But to make it fair, he gives the tortoise a 100-yard head start. The starting gun fires. Achilles blazes forward and reaches the spot where the tortoise started. But during that time the tortoise has crept forward 10 yards. Achilles covers those 10 yards in a flash, but by then the tortoise has moved another yard. Achilles crosses that yard, but the tortoise has gained another 1/10 of a yard. And so on forever. Each time Achilles reaches the place where the tortoise just was, the tortoise has moved a little farther ahead. The gap shrinks, 100 yards, 10 yards, 1 yard, 1/10 of a yard, 100th of a yard, but it never disappears entirely. If you follow the logic step by step, Achilles must complete infinitely many steps before he catches the tortoise. And surely infinitely many steps must take infinitely long. Therefore, Zeno argued, Achilles can never catch the tortoise. Of course, in the real world, Achilles blows past the tortoise in seconds. A toddler knows this. But try to explain exactly where Zeno's reasoning goes wrong, and you will find yourself in surprisingly deep water. Even Aristotle, who spent years attacking Zeno's arguments, could not produce a fully airtight rebuttal. The great Greek philosopher sensed that the paradox involved a confusion about infinity, but he lacked the mathematical machinery to make his intuition precise. The hidden trap in Zeno's argument is the assumption that adding up infinitely many things must produce an infinite total. This feels obvious, and it is wrong. Consider the distances Achilles must cover in the race. 100 yards plus 10 yards plus 1 yard plus 1/10 of a yard plus 100th of a yard, and so on forever. If you add these up, the sum approaches 111 and 1/9 yards. It approaches that number and never exceeds it, no matter how many terms you add. In modern mathematical language, this is called the convergence of an infinite series, and it is one of the most counterintuitive and important ideas in all of mathematics. An infinite addition can yield a perfectly finite answer. The same logic applies to the time it takes Achilles to complete each step. Each step takes a shorter and shorter interval, and the total time converges to a specific finite moment at which Achilles reaches and then passes the tortoise. Zeno's paradox is resolved not by denying that there are infinitely many steps, but by recognizing that infinitely many durations can add up to a finite duration. This concept, the idea that an infinite process can converge to a definite value, is the seed from which all of calculus eventually grew. But the Greeks could not plant that seed. They were terrified of infinity. Greek mathematics was built on the beauty of finite, visible, tangible forms. Perfect circles drawn with compass and straightedge, triangles with rational proportions, harmonies expressed as simple ratios of whole numbers. Infinity threatened to dissolve all of that beauty into chaos. If you allow infinitely small quantities, then you have to ask whether a line is made of infinitely many points that have no length. And if so, how can lengths add up to something? If you allow infinitely many divisions, you must confront the possibility that matter, space, and time are not continuous but granular. And the implications of that were too unsettling for a culture that prized order and harmony above all else. The Greeks were not cowardly for avoiding infinity. They were intellectually honest. They could see the abyss and chose not to jump. There was one spectacular exception, one genius who dared to dance at the edge of that abyss. Archimedes of Syracuse, who lived from roughly 287 to 212 BC. Archimedes is often called the greatest mathematician of antiquity, and it is difficult to argue with that assessment. His contributions to geometry, mechanics, hydrostatics, and engineering were so far ahead of his time that some of his results were not rediscovered until the 17th century. But for the story of calculus, his most important achievement was the method of exhaustion, a technique for calculating areas and volumes of curved shapes by trapping them between sequences of simpler shapes whose areas could be computed exactly. To find the area of a circle, for instance, Archimedes inscribed a regular hexagon inside the circle and circumscribed another regular hexagon around the outside. The area of the circle was trapped between the areas of the two hexagons, which could be calculated using basic geometry. Then he doubled the number of sides, 12-sided polygons, then 24, then 48, then 96. With each doubling, the inner polygon grew a little larger and the outer polygon shrank a little smaller, and the gap between them narrowed. By the time he reached 96-sided polygons, Archimedes had pinned down the value of pi, the ratio of a circle's circumference to its diameter, to between 3.1408 and 3.1429. An impressive feat for a man working without algebra, without decimals, and without a zero symbol. The method of exhaustion is not calculus, but it contains the ghost of calculus. The essential move, approaching a curved truth by squeezing it between increasingly accurate, straight-line approximations, is exactly the move that calculus would later formalize under the name of the limit. Archimedes understood the concept of a limit intuitively, even though the word would not be defined rigorously for another 2 millennia. He knew that as the number of polygon sides increased without bound, the polygon areas converged to the circle's area, and he used this insight to calculate areas and volumes that no one before him had been able to touch. The area under a parabolic arch, the surface area and volume of a sphere, the volume of a cone. His results were stunning, but they remained isolated feats of brilliance. Each new shape required a fresh act of geometric ingenuity. There was no general-purpose algorithm, no systematic method that could be applied to any curve or any changing quantity. The tool was a scalpel, not a machine. And after Archimedes was killed by a Roman soldier during the siege of Syracuse in 212 BC, reportedly while drawing geometric figures in the sand, so absorbed in his work that he did not notice the city falling around him, the flame of Greek higher mathematics dimmed. Rome had little use for abstract geometry, and the intellectual energy of the Western world shifted elsewhere for more than 1,000 years. The flame did not die entirely. Scholars in the Islamic world preserved and extended Greek mathematical knowledge during the centuries when Europe was mired in the so-called Dark Ages. Mathematicians such as Alhazen in the 11th century and later European thinkers such as Nicole Oersma in the 14th century made incremental advances in understanding motion and change. But the decisive breakthrough required a specific historical catalyst. And that catalyst arrived in the 16th and 17th centuries in the form of a scientific revolution that upended humanity's understanding of its place in the cosmos. The old geocentric model of the universe, with the Earth at the center and heavenly bodies moving in perfect circles, was crumbling. The Polish astronomer Nicholas Copernicus had proposed a sun-centered model in 1543, and by the early 1600s, a German astronomer named Johannes Kepler was dismantling the last remnants of the old celestial clockwork. Kepler inherited a treasure trove of astronomical observations from the Danish astronomer Tycho Brahe, who had spent decades making the most precise naked-eye measurements of planetary positions in history. Brahe's data were accurate to about 1 arcminute, an astonishing achievement for a man working without a telescope. When Kepler attempted to fit the orbit of Mars to a circular path using Brahe's data, he found a discrepancy of about 8 arcminutes. 8 arcminutes is a tiny angle, about 1/4 the apparent diameter of the full moon. But Kepler trusted Brahe's data absolutely and refused to ignore the discrepancy. He spent years testing different shapes until he found the one that fit, an ellipse, with the sun at one of its 2 focal points. This was Kepler's first law of planetary motion, published in 1609, and it was a shattering revelation. For 2,000 years, Western astronomy had assumed that heavenly bodies moved in circles because the circle was the most perfect shape, and the heavens were the realm of perfection. Kepler replaced perfection with truth. His second law described how a planet sweeps out equal areas in equal times, moving faster when it is closer to the sun and slower when it is farther away. His third law, published in 1619, established a precise mathematical relationship between a planet's orbital period and its average distance from the sun. The square of the period is proportional to the cube of the semi-major axis. These laws were a monumental achievement, but they had a gaping hole. They described what the planets do, but not why they do it. Kepler could tell you the shape of Mars's orbit and the speed at which it travels at any point. But he could not tell you what force was reaching across millions of miles of empty space to bend the planet's path into an ellipse. The what was answered. The why was wide open. The man who answered the why was born on a farm in rural England on Christmas Day, 1642. The same year Galileo died. His name was Isaac Newton, and by any reasonable measure, he was the most consequential scientific mind in human history. Newton was a difficult, secretive, often vindictive man who feuded bitterly with rivals and spent as much time on alchemy and biblical chronology as on physics and mathematics. But when he turned his attention to the natural world, his insight was almost extraterrestrial in its depth and precision. The pivotal period in Newton's life came in 1665 and 1666, when an outbreak of bubonic plague forced the closure of Cambridge University, where Newton was a 23-year-old student. He retreated to his family's farmstead in Woolsthorpe, a tiny village about 60 miles north of Cambridge, and spent roughly 18 months in near total isolation. During that period, later known as his annus mirabilis, his miraculous year, Newton accomplished 3 things, any one of which would have earned him immortality. He conducted experiments with prisms that revealed white light to be a mixture of all the colors of the spectrum. He formulated the law of universal gravitation, the idea that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. And he invented the mathematical framework that he called the method of flux ions, which the world would later know as calculus. A single young man, confined to a farmhouse by a plague, working largely alone, laid the foundations for 3 centuries of science. Newton needed calculus for a specific reason, to solve the problem of motion. He wanted to prove, mathematically, that his law of gravitation implied Kepler's elliptical orbits. To do this, he needed to track how a planet's position and velocity change from one instant to the next. Because gravitational force depends on the distance between the planet and the sun, and that distance is itself changing continuously. The existing mathematics of his day could handle static shapes, triangles, circles, conic sections, but had no way to deal with quantities that were in a state of perpetual flux. So Newton created a new mathematics that could. His approach was rooted in the same intuition that Archimedes had used, carried to its logical conclusion. To find the speed of a moving object at a single instant, you look at how far it moves in a very short interval of time and divide the distance by the time. That gives you an average speed over that small interval. Then you make the interval shorter and check again. The average speed changes slightly. You make the interval shorter still, and shorter, and shorter. As the interval shrinks toward 0, the average speed converges toward a single definite value. And that value is the instantaneous speed, the speed at one frozen moment. This process of shrinking an interval toward 0 and watching a ratio converge to a definite limit is the fundamental operation of differential calculus. And it is called taking a derivative. The derivative of position with respect to time is velocity. The derivative of velocity with respect to time is acceleration. In one conceptual stroke, Newton had given mathematics the ability to describe motion at its most granular level, instant by instant, not as a blurred average over long stretches of time, but as a precise snapshot of what is happening right now, almost simultaneously and entirely independently. A German mathematician and philosopher named Gottfried Wilhelm Leibniz was constructing the same edifice from a different direction. Where Newton approached calculus through the physics of moving bodies, Leibniz came at it through the geometry of curves. He wanted to find the slope of a curve at any given point, which is the geometric equivalent of instantaneous speed, and the area enclosed beneath a curve, which is the geometric equivalent of total accumulated distance. Leibniz published his results in 1684 and 1686, slightly before Newton's major publication. And this timing ignited one of the most vicious priority disputes in the history of science. Newton's allies in the Royal Society in London accused Leibniz of plagiarism. Leibniz's supporters on the European continent fired back with counter-accusations. The feud consumed both men's later years and poisoned relations between British and continental mathematics for a century. Today, historians are essentially unanimous. Newton and Leibniz invented calculus independently. They arrived at the same destination by different roads, which is actually a testament to the inevitability of the idea. By the late 17th century, the problems that demanded calculus, planetary orbits, trajectories of projectiles, shapes of curves, optimization of quantities, had accumulated to the point where the invention was, in a sense, overdue. If Newton and Leibniz had not created it, someone else would have within a decade or two. Leibniz made one additional contribution that turned out to be just as important as the calculus itself. He invented the notation. The elongated S symbol that represents integration, the integral sign, was first used by Leibniz on October 29, 1675, in an unpublished manuscript. It stands for the Latin word summa, meaning sum, because integration is the process of adding up infinitely many infinitely small pieces. The dx and dy that appear in calculus expressions are also Leibniz's inventions, representing infinitesimally small changes in the variables x and y, Newton's own notation, which used dots placed over letters to indicate rates of change, was clunkier and harder to generalize. It is Leibniz's notation, not Newton's, that the world uses today, and the elegance and suggestiveness of that notation played a significant role in making calculus accessible and powerful. Good notation is not a luxury. It is a cognitive tool that shapes how you think about the ideas it expresses. So now the two great operations of calculus were on the table. Differentiation, the operation introduced by Newton and Leibniz, takes a quantity that is changing and extracts its instantaneous rate of change. If you know how far a car has traveled at every moment, differentiation tells you its speed at any given instant. Integration, the other operation, takes an instantaneous rate and accumulates it over time to recover the total quantity. If you know the car's speed at every moment, integration tells you how far it has traveled in total. One operation dissects, the other assembles. One zooms into an infinitesimal instant, the other zooms out to encompass an entire span. They appear to do opposite things, and this raises a profound question. Why are differentiation and integration bundled together into a single subject called calculus, rather than being treated as two separate branches of mathematics that happen to coexist? The answer is one of the most beautiful and consequential revelations in the history of human thought, and it goes by the name of the fundamental theorem of calculus. To understand it, imagine you are piloting a spacecraft. You fire the engines and begin accelerating. The speedometer on the dashboard shows your velocity climbing. 10 meters per second after 1 second, 20 meters per second after 2 seconds, 30 meters per second after 3 seconds. Your velocity is changing at a constant rate, which means your acceleration is constant. Now consider two questions. First, what is your acceleration right now? To answer this, you look at how your velocity is changing over time. You take the derivative of velocity with respect to time, and you get acceleration. That is differentiation at work. Second, how far have you traveled since you started? If your speed were constant, the answer would be simple, speed times time. But your speed is constantly increasing, so you cannot just multiply. Instead, you chop the journey into tiny intervals. Approximate the distance covered in each interval by multiplying the speed at that moment by the tiny duration, and then add up all those little distances. The finer you chop, the more accurate the total. In the limit of infinitely fine chopping, you have performed an integration. Now here is the key insight. You started with velocity. Differentiating velocity gave you acceleration. Integrating velocity gave you distance. What happens if you differentiate distance? You get velocity back. And what happens if you integrate acceleration? You get velocity. The two operations are exact inverses of each other, like multiplication and division, like encryption and decryption. What one builds, the other dismantles. What one dismantles, the other rebuilds. This is the fundamental theorem of calculus, and its importance cannot be overstated. Before this theorem, integration was a nightmare. To compute the area under a curve, You genuinely had to add up infinitely many infinitely thin slices. A conceptual and computational horror. The fundamental theorem revealed a shortcut of breathtaking elegance to integrate a function. Simply find another function whose derivative equals the original function, and evaluate it at the endpoints. The infinite summation collapses into a single subtraction. Problems that would have taken Archimedes weeks of painstaking geometric argument could now be solved in minutes with a few lines of algebra. This was the tool that unlocked the solar system. Newton combined his law of universal gravitation with the machinery of calculus to derive Kepler's 3 laws of planetary motion from first principles. Gravitation tells you the force on a planet at each instant. Force divided by mass gives acceleration, by Newton's second law, F equals ma. Acceleration is the derivative of velocity, and velocity is the derivative of position. So if you know the acceleration at every instant, you integrate once to get the velocity and integrate again to get the position. Starting from a single equation for gravitational force, Newton could trace the complete orbit of a planet, and the orbit turned out to be an ellipse, exactly as Kepler had observed. This was not merely a confirmation of Kepler's empirical result. It was a deep explanation of why the result was true. Kepler could say that planets move in ellipses. Newton could say that planets must move in ellipses because gravity obeys an inverse square law, and the mathematics of calculus applied to such a law inevitably produces an elliptical path. The gap between description and explanation, between what and why, was closed by calculus. And then something even more remarkable happened. Over the following 3 centuries, as physicists probed deeper and deeper into the fabric of reality, they discovered that virtually every fundamental law of nature takes the same mathematical form. That form is the differential equation, an equation that describes how some quantity changes from one instant to the next. Newton's second law of motion, F equals ma, is a differential equation because acceleration is the second derivative of position with respect to time. It looks deceptively simple, just 3 symbols, but by plugging different force laws into the F, you can describe an astonishing variety of phenomena. The arc of a baseball thrown from the mound at Yankee Stadium, the trajectory of a bullet, the swing of a pendulum, the oscillation of a spring, the orbit of the moon, the path of a comet, the vibration of a guitar string, all are solutions to Newton's differential equation with appropriate forces substituted in. In the 19th century, the Scottish physicist James Clerk Maxwell achieved something that many physicists consider the most elegant accomplishment in the history of science. He unified the phenomena of electricity and magnetism into a single framework described by 4 differential equations, now known as Maxwell's equations. These 4 equations tell you how electric charges produce electric fields, how there are no magnetic monopoles, how a changing magnetic field generates an electric field, and how an electric current or a changing electric field generates a magnetic field. When Maxwell manipulated his equations mathematically, looking for solutions that described waves propagating through space, he found that such waves were indeed predicted by the equations, and that their speed was determined entirely by 2 measurable constants: the permittivity of free space and the permeability of free space. He calculated that speed. It was approximately 186,282 miles per second. That number was already known. It was the speed of light, measured independently by experimental physicists who had nothing to do with electricity or magnetism. The conclusion was inescapable. Light is an electromagnetic wave. Maxwell did not discover this by building a better telescope or by performing a new experiment. He discovered it by solving differential equations. The secret of light had been hiding inside the mathematics all along, waiting for someone to ask the right question and follow the calculus wherever it led. In the 20th century, the reach of differential equations extended still further, into territories so extreme that human intuition fails completely. In 1915, Albert Einstein published his general theory of relativity, which reimagined gravity not as a force pulling objects together across empty space, but as the curvature of space-time itself, warped by the presence of mass and energy. The core of general relativity is Einstein's field equation, a ferociously complex differential equation that relates the geometry of space-time to the distribution of matter and energy within it. Solving this equation is extraordinarily difficult. Einstein himself could not find exact solutions for most physical situations, but the solutions that have been found have revealed a universe far stranger than anyone imagined. The first exact solution came just months after Einstein published his theory, and it came from an unlikely place. Karl Schwarzschild was a German physicist serving on the Eastern Front of World War I when he received a copy of Einstein's paper. Despite suffering from a painful autoimmune skin disease that would kill him within months, Schwarzschild managed to solve the field equation for the simplest possible case: the spacetime surrounding a perfectly spherical, non-rotating mass. The solution, derived in a military tent on the Russian front, is now called the Schwarzschild metric, and it contained a prediction so bizarre that even Einstein doubted it could correspond to physical reality. The mathematics showed that if a sufficient amount of mass were compressed into a small enough volume, the curvature of spacetime would become so extreme that nothing, not matter, not light, not information of any kind, could escape from within a certain radius. That radius is called the event horizon, and the object it defines is what we now call a black hole. Inside the event horizon, the roles of space and time essentially swap. Moving forward in time becomes indistinguishable from moving inward toward the center, which means that once you cross the event horizon, reaching the center is not merely likely but inevitable as tomorrow. At the very center, the mathematics predicts a point of infinite density and infinite curvature, a singularity. For decades, physicists dismissed black holes as mathematical curiosities, artifacts of an overly idealized equation that could never exist in the real universe. They were wrong. In April 2019, the Event Horizon Telescope collaboration, a planet-spanning network of radio observatories, released the first direct image of a black hole. The supermassive black hole at the center of the galaxy Messier 87, located about 54 million light-years from Earth, with a mass of roughly 6.5 billion suns. The glowing ring of superheated gas surrounding the dark shadow of the event horizon matched the predictions of general relativity, predictions derived from Einstein's differential equation, with stunning fidelity. The mathematics had seen the truth a century before our telescopes could. Another solution to Einstein's equation reshaped our understanding of the cosmos itself. In 1922, the Russian physicist Alexander Friedmann applied general relativity to the universe as a whole, treating all the matter in the cosmos as a uniform fluid and solving for how the overall size of the universe changes with time. The result, known as the Friedmann equation, delivered a shocking verdict: a static, unchanging universe is not a stable solution. The universe must be either expanding or contracting. Einstein, who believed deeply in a static universe, was so disturbed by this result that he introduced an extra term into his equation, the cosmological constant, specifically to counteract the expansion and hold the universe still. He later called this the greatest blunder of his career, because 7 years later, in 1929, the American astronomer Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, demonstrated that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. The universe is expanding. Friedmann's differential equation had predicted this expansion years before Hubble observed it. Today, the Friedmann equation, refined and extended by subsequent research, tells us that the universe is approximately 13.8 billion years old, that its expansion is currently accelerating, and that the agent of that acceleration is a mysterious entity called dark energy, which constitutes roughly 68% of the total energy content of the cosmos. Ordinary matter, the atoms that make up stars, planets, and human bodies, accounts for a mere 5%. The remaining 27% is dark matter, another enigma. We can write down the differential equations that describe the universe's evolution with exquisite precision, and those equations tell us that 95% of reality is made of stuff we have never directly detected and do not understand. Calculus, in this sense, is not just a tool for answering questions. It is a tool for revealing how much we do not yet know. The third great theater in which differential equations reign is the quantum world, the realm of atoms, electrons, photons, and the other fundamental particles from which all matter is assembled. In the early 20th century, physicists discovered that the behavior of very small things defies every rule that governs the everyday world. An electron does not orbit the nucleus of an atom the way a planet orbits a star, tracing a clean, predictable path. Instead, the electron exists in a strange cloud of probability, simultaneously everywhere and nowhere until the moment you measure it, at which point it appears at a definite location, as if it had been there all along. Light, which Maxwell had proven to be a wave, also behaves like a stream of particles. Particles, which Newton had treated as tiny billiard balls, also behave like waves. This wave-particle duality, as it is called, is not a metaphor or an analogy. It is a literal description of how nature works at the smallest scales, and it is deeply, profoundly weird. In 1926, the Austrian physicist Erwin Schrödinger proposed a differential equation that brought order to this chaos. The Schrödinger equation describes how a mathematical object called the wave function evolves over time. The wave function is not something you can see or touch. It is not a physical wave in the ocean or in the air. It is a mathematical function that encodes all the information there is to know about a quantum system. If you want to know the probability of finding an electron at a particular location, you take the wave function at that location, compute its absolute value squared, and the result is the probability. The Schrödinger equation tells you how this probability distribution changes from one moment to the next. It is a differential equation because it relates the rate of change of the wave function, its time derivative, to its spatial properties, its second spatial derivative. In other words, the same mathematical structure that Newton used to describe a cannonball and Maxwell used to describe a beam of light and Einstein used to describe the curvature of spacetime also describes the ghostly probability waves that govern the behavior of the smallest constituents of matter. The universality of the differential equation as a form is not a coincidence. It reflects something deep about the structure of the universe itself. Here is what that something is, and it is perhaps the most profound idea in this entire discussion. Nature is local. What happens at a given point in space and time depends only on conditions at that point and its immediate neighborhood, not on what is happening 1,000,000 miles away or what happened 1,000,000 years ago. A planet responds to the gravitational field at its current location, not to the gravitational field at some distant point. An electron responds to the electric and magnetic fields in its immediate vicinity, not to fields on the other side of the galaxy. This locality means that the laws of physics relate the state of a system right now to its state an instant later. The relationship between now and the next instant is all there is. If you know the complete state of a system at one moment, positions, velocities, field strengths, wave function values, then the laws of physics determine the state at the next moment. And from that state, the next moment after that is determined, and so on, cascading into the future. This is exactly what a differential equation expresses. A rule connecting the current state to its instantaneous rate of change. The reason every fundamental law of nature is a differential equation is that nature operates by relating each moment to the next. And the mathematical tool for expressing moment-to-moment relationships is the derivative. Calculus is not merely convenient for describing physics. It is the only language capable of expressing what physics actually is. But this magnificent tool, this language of the universe, has limits. And acknowledging those limits honestly is just as important as celebrating its triumphs. The most dramatic failure of calculus occurs at the heart of a black hole. If you take the Schwarzschild solution and follow it all the way to the center, the equations predict that spacetime curvature becomes infinite, density becomes infinite, and the known laws of physics simply disintegrate. This point of infinite values is called a singularity, and physicists do not believe it represents a real physical state. Instead, they believe it represents the breakdown of the mathematical framework itself. General relativity, for all its spectacular success, is a theory built on the assumption that spacetime is smooth and continuous, that you can zoom in on any region of spacetime and find it looking like a calm, flat sheet. Calculus depends on this smoothness absolutely. The operation of taking a derivative assumes that you can always subdivide an interval into smaller pieces, again and again without limit. But quantum mechanics has revealed that at the smallest scales, nature is not smooth. Energy comes in discrete packets called quanta. Angular momentum comes in discrete units. The electromagnetic field is mediated by individual photons, not by a continuous flow of energy. If space and time themselves are ultimately discrete, if there is a smallest possible length and a smallest possible duration, then the assumption of infinite divisibility on which calculus rests is a fiction, a spectacularly useful fiction that works beautifully at human scales and astronomical scales, but breaks down in extreme conditions. The scale at which this breakdown is expected to occur is called the Planck scale. The Planck length, approximately 1.6 times 10 to the negative 35 meters, is unimaginably small. To put it in perspective, an atom is to the entire observable universe roughly what the Planck length is to the diameter of an atom. At distances this small, the smooth, continuous spacetime of general relativity is expected to dissolve into something fundamentally different. Perhaps a foaming quantum froth of geometry, perhaps a discrete network of interconnected nodes, perhaps something entirely beyond our current imagination. We do not know, because we do not yet have a theory that successfully combines general relativity with quantum mechanics at the Planck scale. This missing theory, often called quantum gravity, is the most sought-after prize in theoretical physics. Calculus hit another wall in the development of quantum electrodynamics, or QED, the quantum theory of how light and matter interact. When physicists in the 1930s and 1940s tried to calculate basic properties of the electron using the Schrödinger equation and its relativistic successor, the Dirac equation, they kept getting infinite answers. The mass of the electron came out infinite. The electric charge of the electron came out infinite. Every calculation that ventured beyond the simplest approximation exploded into meaningless infinities. The crisis was resolved in the late 1940s by three physicists working independently: Richard Feynman at Cornell University, Julian Schwinger at Harvard, and Shinichiro Tominaga in Tokyo. Each of them developed a technique called renormalization, a method of systematically absorbing the infinite quantities into redefinitions of measurable parameters like mass and charge. The process is mathematically rigorous but philosophically unsettling. You are essentially sweeping infinities under the rug and arguing that the rug is reality. Despite this conceptual unease, renormalized QED turned out to be the most accurate theory in the history of science. The magnetic moment of the electron, calculated using QED, agrees with experimental measurements to more than 10 significant figures, the equivalent of predicting the distance from New York to Los Angeles and getting it right to within the width of a human hair. Feynman, Schwinger, and Tominaga shared the Nobel Prize in Physics in 1965 for this work. But the fact remains that the infinities arose because the differential equations of QED assumed a smooth, continuous spacetime with no smallest scale. Renormalization tamed the infinities without explaining them. Many physicists suspect that a true theory of quantum gravity will not merely tame the infinities, but eliminate them by replacing the continuous spacetime of calculus with something more fundamental. Several candidate theories of quantum gravity are currently under investigation. Loop quantum gravity proposes that spacetime at the Planck scale is not a smooth continuum, but a network of discrete loops called spin networks, in which area and volume come in quantized chunks. If this picture is correct, then the singularity at the center of a black hole is not actually a point of infinite density, but a region of extremely high but finite density. And the laws of physics remain meaningful there. String theory proposes that the fundamental constituents of nature are not point particles but tiny vibrating strings or membranes, and the different modes of vibration give rise to the different particles and forces we observe. Both of these approaches are mathematically sophisticated and physically provocative, but neither has been confirmed by experiment. The energies needed to probe the Planck scale directly are so absurdly high, roughly a billion times the energy of the most powerful particle accelerator on Earth, that direct. Experimental tests may be impossible with foreseeable technology. Theoretical physicists are searching for indirect signatures, subtle effects that might show up in the cosmic microwave background radiation or in the gravitational waves from merging black holes. But so far the Planck scale remains a locked door for which we have not yet found the key. What is remarkable about this situation is that calculus itself pointed us to its own limitations. The singularities that appear in general relativity are not bugs in the theory. They are messages from the theory, warning signs that say, beyond this point, my assumptions break down and you need a better tool. Calculus is honest about its own boundaries, which is more than can be said for most tools. Knowing where a map ends is just as valuable as knowing what the map shows, because the blank space at the edge of the map is where the next great expedition must go. Let us step back now and survey the full landscape of this story. It began with a question: how fast is that shooting star moving right now? And that question led us through 25 centuries of intellectual struggle. Zeno in ancient Italy sharpened the paradox of infinite division and forced humanity to confront the weirdness of infinity. Archimedes in Syracuse developed the method of exhaustion and showed that curved truths could be approached through straight-line approximations pushed to their limits. Kepler, poring over Brahe's data, discovered that planets move in ellipses and thereby posed the question that demanded calculus. Why do they move that way? Newton, isolated by plague in an English farmhouse, invented the method of flux ions and used it to prove that gravity explains Kepler's laws, connecting the fall of an apple in his orchard to the orbit of the moon around the Earth with a single mathematical principle. Leibniz, working in Germany, arrived at the same mathematics independently and gave it the elegant notation that the world still uses. Together, they established the fundamental theorem of calculus, the deep unity of differentiation and integration, and thereby gave humanity a tool of incomparable power. After Newton and Leibniz, the tool was applied with explosive force across every domain of science and engineering. Maxwell used differential equations to unify electricity and magnetism and discovered that light is an electromagnetic wave. Boltzmann used them to found statistical mechanics and explain how the macroscopic properties of matter, temperature, pressure, entropy, emerge from the microscopic motion of atoms. Einstein used them to describe how mass warps spacetime and predicted black holes, gravitational waves, and the expansion of the universe. Schrödinger used them to describe the quantum behavior of matter and founded the theoretical framework on which all of modern chemistry, materials science, and semiconductor technology depends. Dirac used them to predict the existence of antimatter, which was confirmed experimentally just 4 years after his prediction. In every case, the pattern was the same: write down a differential equation that captures the local, moment-to-moment rules of nature, solve the equation, and watch as the solution reveals the global, large-scale behavior of the universe, often in ways that defy intuition and confound expectation. Today, calculus underpins technologies so ubiquitous that we forget they depend on it. The GPS in your phone works by receiving signals from at least 4 satellites orbiting the Earth at an altitude of about 12,550 miles. Each satellite carries an atomic clock accurate to about 1 nanosecond, and your phone calculates its position by measuring the tiny differences in arrival times of the signals from different satellites. But the calculation must account for the fact that time runs slightly faster on the satellites than on the ground, because the satellites are higher up in Earth's gravitational field, where spacetime is less curved. This correction comes directly from Einstein's general relativity, which is written in the language of calculus. Without that correction, GPS positions would drift by about 6 miles per day, rendering the system useless. Every time you use your phone to navigate to a restaurant or find a gas station, calculus is working silently in the background, reconciling the curvature of spacetime with the ticking of atomic clocks to put you within a few feet of your destination. Medical imaging technologies like MRI and CT scans depend on calculus. An MRI machine detects the tiny magnetic signals emitted by hydrogen atoms in your body and uses a mathematical technique called the Fourier transform, which is rooted in integral calculus, to reconstruct a detailed 3-dimensional image of your internal organs. A CT scan takes hundreds of X-ray images from different angles and uses a mathematical algorithm called the radon transform, another creature of calculus, to assemble them into cross-sectional slices. The image your doctor examines is not a photograph. It is a solution to an integral equation. Machine learning and artificial intelligence, the technologies reshaping the modern economy, depend on calculus at every level. Training a neural network means adjusting millions of numerical parameters to minimize a measure of error. And the algorithm that performs this adjustment, called gradient descent, works by computing derivatives, the fundamental operation of calculus, to determine which direction each parameter should be nudged. Every recommendation Netflix makes, every sentence a language model generates, every face a security camera recognizes, is the output of a process that involves taking derivatives millions or billions of times. Aerospace engineering, weather prediction, ocean current modeling, population genetics, epidemiology, financial modeling, electrical circuit design, audio signal processing, video compression, robotics, bridge construction, dam engineering, nuclear reactor design. The list of fields that depend on calculus could fill this entire text and still be incomplete. The tool that Newton and Leibniz forged in the 17th century has become so thoroughly woven into the fabric of modern life that removing it would be equivalent to removing electricity. Civilization, as we know it, would cease to function. And yet, for all its power, calculus remains, at its core, a simple and beautiful idea. It is the idea that you can understand a continuously changing process by zooming in until the change becomes so small that it is almost zero. Measuring the ratio of change to interval at that extreme magnification, and then zooming back out by accumulating infinitely many of those tiny ratios to recover the behavior of the whole. Zoom in, measure, zoom out, accumulate. That is the rhythm of calculus, and it is the rhythm of the universe, which builds its grand structures, galaxies, stars, planets, oceans, ecosystems, organisms, from the relentless accumulation of infinitesimal changes happening at every point in space and every instant in time. The next time you look up at the night sky and see a streak of light, you will know something that Zeno did not know, something that Archimedes reached for but could not quite grasp, something that Newton and Leibniz brought into focus and that 3 centuries of physicists have used to read the deepest secrets of reality. You will know that the universe is a book written in the language of change, and that calculus is the pair of eyes that lets you read it.